Nuclear chemistry has been extremely resourceful in medical technology and imaging in recent years. Advancements such as PET scans utilize radioisotopes, gamma rays, and positrons to get digital 3D images of different parts of the inner body, most commonly the brain.
PET scans originated in Boston around 1950 by Gordon Brownell with his idea of using radiation for medical purposes, specifically imaging. He invented the first positron imaging machine, although many advancements and improvements have been made since then. 62 years ago, in 1953, Gordon used his scanner to locate a brain tumor in a 7-year-old girl. At this time, Brownell was 1/3 of an inch off from the tumor, but with today's modern scanners, doctors are able to pinpoint exact locations. PET scans became widely used in the year 2000.
PET, or positron emission tomography scans, are used to identify and locate tumors and cancer, as well as monitor blood flow, oxygen intake, effectiveness of cancer treatments, and brain disorders. PET scans, on average, are 20% to 30% more accurate than conventional imaging systems, such as CTs, X-rays, or MRIs. PET scans are also use a stronger amount of radiation, and therefore are able to identify cancerous cells in tissue much earlier than traditional imaging resources.
This is a massive grade 4 astrocytoma. I want you to take a look at it. Really look. Look at its size. Look at the way it invades healthy tissue. Look at its vasculature. It is blood and tissue and flesh.
When a patient gets a PET scan, a nurse injects them with radioactive glucose tracers, usually in the arm. The tracers spread throughout the body over the course of about an hour before the scan takes place. The radioisotopes are pulled stronger towards areas and tissues with more glucose. Positrons react with other electrons to produce gamma rays. Once the positrons have produced the gamma rays are shot around the 360 degrees around the ring. This allows the creation of a 3D image. Scans are monitored digitally and later printed for use during surgery.
I know this is hard, but I need you to not move.
I think I might be done. Am I done?
Not quite yet. Try focusing on your breathing.
I'm not usually like this.
Whenever the affected tissue is located, the cancer cells consume the sugar from the tracer, which releases positive charged particles called positrons. Each positron soon combines with a free electron inside the body, and both particles annihilate, producing a pair of photons. The photons move in opposite directions, drawing a straight line if neither of them is scattered. Millions of photon pairs are emitted and reach the ring detector. The photons intersect with the ring walls, marking the ends of their straight lines. The intersection of several lines marks the exact location of high isotope concentration. The more active the cancer cell is, the more sugar it consumes, the higher the concentration of isotopes, and hence the higher the rate of positron emission. The collection of hundreds of millions of points allows sophisticated computer software to build a 3D, fixed image, or 4D changing over time model of cancer tissues and their concentration.
And I want to get out of here early to get to the game.
Me too. I'm good with that. Let's just do what he said.
Make sure he's on broad spectrum antibiotics. You booked an OR?
Wow, it didn't hit any brain matter at all? Doesn't look like it from this.
How long till Shepard gets down here to take a look? He should be out of surgery any minute. Good. As long as that thing stays in there, the higher the risk of infection or abscess formation.
So, now can